Yeah, welcome. I am Imo Solale Kankemi by name. I'm speaking from Usca San Carlos, Brazil. I'll be presenting on intermolecular forces with a abbreviation of IMFs. Thanks to Professor Dr. Jam Marcel Gallo for this wonderful opportunity. My first slide is going to talk about my introduction. What do I mean by intermolecular forces, in which I termed as definition? I'm going to talk about the definition of intermolecular forces. Intermolecular forces are forces that hold molecules together. For my pictorial illustration, I was trying to illustrate how intermolecular forces is shown diagrammatically. These are the forces. They hold molecules together, and it can either be repulsive or attractive. I want us to take note of that. They are generally weaker than covalent bond. What do I mean by covalent bond? It simply implies intramolecular forces. In my pictorial illustration, I was trying to illustrate intermolecular forces and intramolecular forces. I don't want us to get confused. There are differences between intermolecular forces and intermolecular forces. Intramolecular forces is stronger than intermolecular forces. So this is intermolecular forces, this is intramolecular forces. Please let us not be confused. I don't want us to be confused with that. Intermolecular forces are accountable for the properties of substances. Yes, intermolecular forces tells us much more about a substance. It tells us if they are liquid, if they are solid, or gas at room temperature. So it gives us much more details about the substance. Intermolecular forces are sometimes called van der Waals forces. I want us to take note of that as well. Now to the brief history of intermolecular forces. Someone really did an Herculean task, and the name of the person is John Diderik van der Waals. So he was the one that gave rise to the so-called intermolecular forces. He was born in November 23, 1837 in Leiden, Netherlands, and he was the first to postulate intermolecular forces, developing a theory to account for properties of real gases. This man studied the effect of intermolecular forces on the behavior of real gases. That is why I'm here presenting on intermolecular forces. He was the one that worked to discover that in 1837. My next slide, I will be talking about types of intermolecular forces. We are having various types of intermolecular forces, but I was able to talk about 7 types. In my presentation, I'll be talking about 7 types of intermolecular forces, in which I then segregate or I then group into 2 aspects. We have the van der Waals forces section, and we have other intermolecular forces section. So under the van der Waals forces section, I talked about dipole forces, dipole-induced dipole forces, London forces, which is known as dispersion forces, and I also made mention of ion dipole interaction, ion-induced dipole interaction, hydrogen bonding, Aeon interaction under other intermolecular forces. Now, my next slide, I will take them step by step by discussing what do I mean by dipole forces. Please follow, because I'm talking about 7 types. So the first one is dipole forces. What do I mean by dipole forces? That is, these are the forces that occur between 2 molecules. When they come together, they come in close proximity. They feel an interaction. So in these dipole forces, they are attractive force that is existing between 2 polar molecules. And talking about the 2 polar molecules, these are them: a polar molecule and another polar molecule. What do I mean by polar molecule? It means that it's having an electrical poles. These are the electrical poles, negative, partially positive. So these 2 forces arrive due to the interaction between the opposite charge at the end of the polar molecule. Remember, I said, what do I mean by polar molecule? I said, yeah, it means that they have an electrical poles. So because of the electrical poles they are having, they tend to attract each other. So the opposite charge tends to attract to each other. So the partial charge of one polar molecule can interact. They interact with the opposite charge of the other of the neighboring molecule, giving rise to what? The dipole interaction. So I illustrated side by side and hand by hand. So they can occur in 2 forms. Look at now. This is side by side, positive, partially negative, attracting with partially positive attracting with partially negative. That's for side by side. It can also exist as end by end, partially negative, partially positive. Partially negative attracting with partially positive. Now, and I said both are energetically favorable. And I made note, I said note, polar molecules attract each other by the interaction between what? The partial charge of their electric dipoles. Now to my next slide. I made it well known. I was using like a structural way, the skeleton. Now I'm putting the flesh so that we can understand much more. By adding the flesh, I'm trying to illustrate how dipole-dipole force take place using HCl as an example. Hydrogen is partially positive and chlorine is partially negative. Look at how the dipole-dipole force takes place. The hydrogen tends to, the partially positive tend to what? Form a dipole force with the chlorine. While the hydrogen here as well, partially positive, tends to form what? Another dipole force with the chlorine. I used carbon monoxide as well as example. That's partially positive and partially negative. We can see the dipole force. The partially positive tends to what? Form a force with partially negative. Now, this is another one, HBr. Note, because there is an unequal sharing of electron between the above atom, the partial positive and partial negative are referred to as what? As dipole, which I explained earlier. And I said dipole interaction is weaker than Aeon interaction. Yes, we are going to explain this in the next slide, what Aeon interaction simply implies. Why dipole is it weaker? It is weaker because this one, they donate partial charge, but Aeon they tend to attract with each other. They are permanent, the permanent own number charge. So, but we'll explore more on that in the next slide when we encounter that. Now going to the sixth slide, which is the second type of intermolecular forces, dipole-induced dipole. Even with the way the name illustrated, we should be able to understand the term induced, that is to initiate something. So what do I mean by dipole-induced dipole forces? When a molecule with a polar covalent bond approaches second molecule that contains purely covalent bond. So this is a polar molecule. So, and I said in the bracket, I said permanent electric dipole moment. It's having charge, positive and negative. But this one is non-polar molecule. So this charge tends to what? Induce this. So it tends to induce temporary dipole moment in the second molecule. So the weak electrostatic interaction form is what is now termed dipole-induced dipole bond. So this is the result of the two molecules interacting and causing one of the molecule electron to have distorted charge. So this partially negative is a permanent dipole. The permanent dipole simply implies it's a polar molecule. So why this one is not having any charge? Because it's not having any charge, this permanent dipole, a polar molecule, induce the dipole in a non-polar molecule. So it tends to induce that, making it to have an electron. So I explore more. Whatever I'm doing, I'm showing the skeleton. It's just like a skeleton. And from there, my next slide, I will show the flesh. I will add flesh to the skeleton. Now I'm adding flesh to the skeleton. Example, an oxygen gas can dissolve in water because the permanent dipole in water can induce a dipole in oxygen. Look at what is happening. This is water, partially negative, partially positive, partially positive. Look at an oxygen gas with no electron. Because it is nearer to oxygen gas, it tends to what? Induce a permanent. There's difference between temporary, please take note. Permanent dipole and temporary dipole. So in which it give rise to what? Positive charge and positive. It was embedded how this oxygen gas tends to what? Attain an electron. So that is what we know is called dipole-induced dipole. So example 2, non-polar iodine dissolved in polar ethanol due to dipole-induced dipole forces. So this is the pictorial illustration. Now to my next slide, I'll be talking about London forces. So this is mainly non-polar molecule. So, and I think it's known as the weakest, in which we also call it dispersion forces. At first, the man that gave rise to what we know as London forces, his name is Fritz London. This is a pictorial from 1900 to 1954. So he's dead by now. Fritz London was the man, sorry, I made a mistake here, was the German-American physicist who first explained the force. So the London force is called the Dispassion force. I made mention it's also known as Dispassion force. They are the weakest attraction force that form due to temporary dipole induced a non-polar molecule. So it exists between two molecules that only have covalent bond or non-polar bond. So, this force is also called induced dipole interaction. So if we don't want to call it London force, if we don't want to call it dispersion force, we can also call it induced dipole interaction. So it's important to take note that electrons around the nucleus of atom are in motion. So whenever we're having electron around the atom, they moved around. So this electron does not remain in the stationary phase. So meaning that electron density and electron cloud around the atom in the molecule always fluctuate and with respect with time. So the fluctuation leads towards instantaneous dipole movement. So when two molecules with instantaneous dipole movement are in close contact, they attract one another via an electron force in which the bond is termed London force. I think what I'm saying is a little bit abstract. Let's go to a diagrammatical illustration. So using neon as an example, I used neon as an example. This is neon. So electrons are evenly distributed like what I said in slide 8. So because they are evenly distributed, so their electron cloud is still intact. So, but when neon come together, when we have two neon, look at what will happen. The electron cloud tends to destroy. So, tends to destroy. When the electron cloud tends to destroy, more electron will be moving to this side, which will form partially negative and partially positive. So because of that, the movement of the second neon, the movement of the electron, we tend to what? We tend to move to this side. That is, electron will tend to move to this side so that they can form what? A temporary dipole. That's why I said it's a weak. Please let's take note. It's a weak force. So they tend to form an interaction so that they can form a London forces because they are nearer to each other. So that's just a little bit explanation about that. So I made mention, I said the two molecules with instantaneous dipole movement are in close contact. They attract one another via electron force in which the bond is termed London forces. So that is what happened pictorially here. Now going to the fourth one, which is Aeon dipole interaction. Aeon dipole interaction. An Aeon dipole interaction is an attractive force that results from electrostatic interaction between Aeon and a polar molecule that has a dipole. That is, Aeon and a polar molecule interact. This is an Aeon and this is a polar molecule. I explained. Please let's not forget polar molecule. It means that it has electrical poles. So anyone that has electrical poles is known as polar molecule. But this one is an anion, negative, cation, positive. So an Aeon is an element with charge. An Aeon is an element with a charge that can be referred to as cation or an anion. So that's what we call an Aeon. So a negative Aeon, which is here, attracts partially positive end of a neutral polar molecule. So we can say that this negative Aeon tends to attract a polar molecule. That's why we call it Aeon dipole interaction. And a cation tends to attract negative because it is positive. So this is the skeletal aspect, the skeleton. I will show the addition of the flesh. We can see sodium Aeon tends to form an higher Aeon dipole interaction with a molecule, that is with water rather. So and water is dipole, that is a polar molecule. So this is how the interaction from. So sodium Aeon tends to attract with the oxygen, which is partially negative. So it's now form Aeon dipole interaction. So from the diagram above, I said because water is a polar molecule and has a partial negative and partial positive poles, the Na plus, sodium plus, will form an Aeon dipole interaction with the partial negative part of the water, which is what I explained earlier. So the Aeon dipole interaction is most commonly found in solution. Let's take note. This interaction, the Aeon dipole interaction, is most commonly found in what? Solution. Going to the 12th slide. Below show the explicit version of Aeon dipole interaction. I made it much more explicit, the Aeon dipole interaction. And I said, note, Aeon dipole interaction becomes stronger as either the charge on the electron increase or as the magnitude of the dipole of the polar molecule increases. Look at now. I talked about cation and anion. Look at Cl minus. Look at how it forms Aeon dipole forces with water. So it forms an Aeon dipole interaction with water. You can see hydrogen, which is partially positive, tends to what? Attach with what? Cl minus, which is what? Negative. So this water, they tend to form what? Aeon dipole interaction. So this is a water molecule, the chloride ion. They form Aeon dipole interaction with the chloride ion. And using sodium, Na plus as an example, that is the sodium ion as an example, you can see water as well. That is the water molecule which is polar. They tend to form what? Aeon dipole interaction as well, but in a different way. They make sure that they donate their partially negative to form the interaction, while here they donates the partially positive to create the interaction. Aeon dipole interaction, hydrogen force, dipole, and London forces. So now the reason why I arranged this like this is the mode at which they are stronger. This is much more stronger than hydrogen. Hydrogen is much more stronger than dipole. Dipole is much more stronger than London force. My next slide, which is Aeon induced dipole interaction, which is the 5th type of intermolecular forces I'm talking about. I'm left with 2. An Aeon induced dipole interaction consists of an Aeon and non-polar molecule interacting. Yes, we can see this is an Aeon and this is a non-polar molecule interacting. The other one I talked about, Aeon dipole interaction, that one is having an electrical pole, but this one is not having an electrical pole. So an Aeon induced dipole attraction is a weak attraction that results when the approach of an Aeon induce a dipole in an atom or in a non-polar molecule by disturbing the arrangement of electron in the non-polar species. It looks abstract. I will explain using phases. Talking about phase 1, we are having a positively charged Aeon. Like I said, Aeon induced dipole interaction. This is the Aeon. This is the induced. We want to induce this. So because this is plus, look at what will happen. Electrons are distributed evenly. Normally, this is the electrons are distributed evenly, but because this is a positive Aeon, the Aeon present will make the neutral non-polar molecule electron cloud to be distorted. So now the electron cloud will be disturbed. It will be affected. Why? Because the electron feel the force of attraction from this charged Aeon. So this is from phase 1. It is all right like this. They just feel the attraction. Look at what happened in phase 2. Lot of electron will now be what? Will now be on the left. Look at. But note, it is a lot of electron that will be on the left due to what? The force that they get from this. That is, they get from this positively charged Aeon. So I explained. I said what we now have is an induced dipole. That is, we are inducing it. We are the one causing it. So the Aeon is the same, but the atom on the right has been what? Polarized. This is the Aeon. It is the same. I'm sorry. And this atom here, it has been polarized. So therefore, the left side of the atom will have a partial negative charge. You can see the negative charge due to what? The positive charge that is here. So I showed it in phase 3, which is my next slide. While the other side will have what? A partial positive charge. So look at phase 3. This is what now happened. The Aeon already induced the charges here. So the partial positive charge tends to come and form what? Ion induced dipole interaction. So it induces it to have these charges here and have these charges here. So temporary induced dipole, because we create it, so we can call it a temporary induced dipole. We are the one that initiated it. So which now arise as two regions. So pictorial illustration of Aeon induced dipole. I use ion 2 plus, ion 2 plus, which is an oxygen, partially negative, O2, partially positive, partially negative. So this is ion induced dipole. We induce that. So now going to hydrogen bonding. So hydrogen bonding is a special type of dipole-dipole interaction between the hydrogen atom in a polar molecule and the highly electronegative atom in another molecule. I will explain what I imply by that. So this hydrogen bond is an electrostatic force of attraction that exists between two covalently bonded hydrogen atoms of one molecule and the electronegative atom of another molecule. So it's simply the attraction of positively charged hydrogen and negatively charged lone pair of electron. So, and take note, the electronegative atom, we have nitrogen, fluorine, and oxygen. So this hydrogen bonding tends to attract himself with what? Electronegative atom. Oxygen is an electronegative atom. Nitrogen is an electronegative atom. So hydrogen tends to bind with fluorine, hydrogen tends to bind with oxygen, and hydrogen tends to bind with what? Nitrogen. So we can see, I use water molecule as an example. We see water molecule is very good example of substance that exhibits hydrogen bonding. Look at hydrogen. Hydrogen tends to bind with what? Oxygen. It tends to bind with the lone pair of electron. So the lone pair of electron of oxygen is attracted to the positive nucleus of hydrogen atom, forming hydrogen bond. So it forms hydrogen bond due to what? The attraction of hydrogen to electronegative atom. So all the epistle I wrote here that I bullet my points 1, 2, 3, it's just trying to explain how hydrogen tends to form electronegative hydrogen bonding tends to form with electronegative atoms. So these are the three atoms. So my next slide, I made it known hydrogen atom attached to a highly electronegative atom. Hydrogen atom attached to unshared pair of electron on the electronegative atom. It's good to take note of this, please. The unshared pair of electron, which is what I explained here. You see, the hydrogen tends to bind with the unshared pair of electron. So that is why we can't have three hydrogen here, because we are having oxygen is having two unshared pair of electron. So this hydrogen here bind with this hydrogen here bind with this unshared pair of electron. Now, going back to this, we can see, I used hydrogen and oxygen here. So now I want to use hydrogen and fluorine and hydrogen and nitrogen, which I will show in my next slide. You can see hydrogen bind with nitrogen as well. Hydrogen bind with what? Oxygen of shared pair of electron. Why? Hydrogen also bind with what? Fluorine on shared pair of electron. So which is what we term hydrogen bond. So that's just that for hydrogen bonding. And now I made it much more pictorial. I used pictorial illustration this time around. Hydrogen bonding. You can see how hydrogen binds with oxygen. Hydrogen binds with what? Oxygen. Oxygen, hydrogen, oxygen, hydrogen. So we can see the way hydrogen tends to form is what? It's bond by attracting what? Electronegative atoms. Now the last one, which is known as Aeon-Aeon interaction. Aeon-Aeon interaction are an attractive force between ions with opposite charges. Here is quite different from dipole-dipole forces that I made mention in my first slide. Talking about dipole-dipole forces, they donate partially negative and partially positive. But Aeon-Aeon interaction is quite stronger than that, because permanent whole number charge is a permanent whole number charge. It donates its electron. So the 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 positive Na plus tends to what? Bind with, the Na plus tends to bind with what? The Cl minus, sodium minus. So the permanent whole number charges. And note, if we are having Na plus here and we are having let me say S2 minus, the Na plus and S2 minus is quite stronger than Na plus and Cl minus. Why? Because Na plus is plus 1 and this one is minus 1. So the other one, which is Na plus, will be what? Plus 1 and minus 2. So the higher the charges, the stronger it becomes. So it is good to take note that Aeon interaction is quite different and stronger than dipole-dipole forces, because the dipole-dipole forces donate partial charge of its electron in order to bind. But here it's so simple. The Na plus tends to what? Conjugate, combine together with Cl minus, giving rise to NaCl. So obrigado, thanks. I think I was able to create a great impact by explaining painstakingly about intermolecular forces. I was able to talk about the 7 types of intermolecular forces that we have, which implies dipole-dipole forces, dipole-induced dipole forces, the London forces, which is also known as dispersion forces, and also we can also call it induced dipole forces. And also the fourth one, I talk about Aeon dipole interaction, and the fifth one I talked about Aeon induced dipole interaction, and the sixth one I talked about hydrogen bonding, and lastly I talked about Aeon interaction. So I was able to differentiate between the 7 types of intermolecular forces, and I made mention of the person that postulated, that is the person that gave rise to me talking about intermolecular forces presently. Thank you very much.